We rolling? We rolling? We live. We're live. There it is. There's my YouTube notification. Welcome, everybody. I'm trying to get next week's meetup here. What? Can't remember the exact title. Yeah, something like that. Get it here. Oh, yeah. So it's going to be Zach. Is Zach here today? No. But anyway, it's Hey Lodash, you're doing it wrong. That's next week's. That'll be fun. Hopefully get to hear some trash talk. Sponsors, we finally got Squid up here. Anybody from Squid? Yeah, represent. All right, thanks, Squid. Our newest sponsor. And thanks to all the rest who helped make this possible. If you didn't know, these fine folks provide pizza and other food options for you every week. So, without further ado, Tom works at Delegator. Delegator, right? Yeah, oh yeah, that's right. Don't let me forget. Come on up here.
Brett always lets me pitch my meetup. It's Cha DevOps. It's next Tuesday night at 6. We'll be in the accelerator space. We're going to start partnering once a quarter with Red Hat, and they want to start a user group in Tennessee, and they want to have a Chattanooga division in Nashville, a Knoxville, and a Memphis. So the inaugural one is next Tuesday night. It's Red Hat / Cha DevOps, and it's going to be on automation. They're going to bring a speaker to talk about Ansible, the community project, and where it stands now after it's been bought by Red Hat and what they're doing with it. They're doing a bunch of stuff with it. It's even going to be in the OS, at the OS management level on Red Hat 8. So I thought that was pretty interesting. We'll also have an executive from Unum who's going to kick us off with a keynote and talk about automation that we're doing there at Unum. We're going to have a couple other customer testimonials, and then the presentation they're going to bring beverages and pizza and swag. So I hope you can make it. It's Cha DevOps on Meetup, and it's next Tuesday night right over there at 6. Thanks.
All right, so there you are. Everybody give a round of warm applause, Tom.
Thank you, Brent. Hi, everyone. Thank you for being here. My name is Tom Richards, and I'm a developer. I work for Delegator. Delegator is a digital advertising agency here in downtown Chattanooga. I'm a huge fan of Arch Linux, as you can tell. It's my go-to distro for day-to-day work. So starting things off here, quick show of hands. How many of you have heard of the Crystal programming language? So like 40% roughly, something like that. So for those of you who have heard some stuff about this, maybe you've seen a presentation online, this is gonna all sound pretty familiar. I'd like to also give a shout out to Brian at Manas for letting me borrow these slides for this presentation. And the first thing I'd like to do is start off with a couple of quick demos just to show you the types of things that you could build with the Crystal programming language today. Nothing too heavy. The first one here is Conway's Game of Life. It's just a simple little command line application. Wow, look at it go. It's lovely. Yeah, so nothing too special, but you got console output. It's great. The second example here is a ray tracer. So this is a program that's using SDL, the graphics library, with OpenGL to render a 3D scene in real time. So this guy right here is not a static image. This is just a graphics depiction of a scene, and it was rendered here in software. So these are just a couple of sample programs that were included with the Crystal compiler in the repository. So there's a whole bunch more. If you want to go take a look at those, they do exist. And for any other code samples you might see in this presentation, I would point you over to this website. It is a compile and run code in Crystal site. So you just type in your code and you click the big compile and run button. The server will compile your stuff and send you the results. It's really great. No installation required. So the motivation for a new language. Why do we need another language? We've already got all these great languages coming out, right? We've got Swift and Rust and JavaScript. Why do we need something like this? So I want to give a little bit of a backstory for. So maybe you work for an agency like I do, or maybe you're writing an app in-house, and you've chosen to write this app in a nice language, like a solid one, like a Java or a C#. and you've taken the route that many agencies or other developers have, and you jump aboard this dynamic language bandwagon, right? Well, it's really great to not have to do all that ceremony, right? I don't have to write all my getters and setters, and I don't have to write all these types, blah, blah, blah. And so we might jump to something like Ruby. This is my personal preference for a dynamic language. It's very lovely language. It has a great community. It's very productive, very practical. But the problem here is that it's really not known for its speed, right? Much like other dynamic languages, optimized for the joy of the developer, right? Not the joy of the computer so much. So it's pretty well known that compiled languages are more efficient than other interpreted ones. And the other thing that we miss from our Java and C# like universe is we miss having the safety nets, right? We have these big apps that we've started to grow in size, and we want to do a big refactor. And oh man, you know what I really miss? I miss having that type checking at compile time. That's the thing that I miss. And I think the recent surge of like third-party static type checking tools. So we have, in JavaScript, we have things like Flow and TypeScript. PHP just recently improved what they call, type hints. For Erlang and Elixir, we have things like Dialyzer, right? This is not an accident. This is people who are all saying the same thing, like, holy cow, I really missed this from my compiled languages. So what if we could have it all, right? What if we had all of these things? And so that's where Crystal comes in. And so to give you just a quick overview of the syntax here, if you're familiar with Ruby, this should look very familiar to you. So this Crystal snippet here is practically Ruby code, maybe with just one small exception here. You've got this type annotation there. But otherwise, very Ruby-like. We have instance variables declared with an @ sign. The constructor method is named initialize. You have string interpolation with our octothorpe and curly braces there. So yeah, very heavily inspired by Ruby, but compatibility with Ruby is not exactly a goal. So sometimes you might have, just by coincidence, the fact that your Crystal code can run in the Ruby interpreter, but that's not a goal of the project. And one final thing about the type annotation, if that's scary, we only see one of those here, and that's necessary for the program to compile, but like, when you think about it, it could be a lot worse, right? We could have like 4. We could have a type annotation for the return value of this constructor, and a type annotation for that instance variable. And so one of the things that we talked about that we wanted in our language is we want the compiler to do some smart type checking for us. So like, let's say that we made a silly mistake like adding a string and an integer together. Right? In Crystal, this code will be compiled when we run Crystal build, but it's not executed because the compiler tells us this nice error message, and it says, hey, there's no overload allowed for that method on this particular line, right? You can't do that thing. That's nice information. So, if you're like me, I would never make a silly mistake like that. That's just not something I would do, right? What about something less trivial? So here we have a piece of Crystal code, and this one is compatible with Ruby. So if you ran this through the Ruby interpreter, you would get some output. Wow, that's great. Look at that. The program works, and it runs, and everything is fine because our test passed, and the CI ran, and it's all great, and there's no way that this could ever go wrong, right? Well, maybe not so much, right? What happens when we hit the off chance of that random returning a different value, right? So we have this blow up in runtime here where our code did something that we didn't expect, and we knew that runtime error was going to occur, right? Why couldn't the compiler check that for us? And so in Crystal can help us out here. Crystal in all of its types are non-nillable by default. So when we try to run this code, it will compile it first, and then it'll give us this nice error message that says, hey, by the way, you goofed. Here is where you goofed. And this has got to be my favorite part right here, the caret and tilde underline right there. It'll tell you exactly where you went wrong. I love that they copied that feature from Clang. I think Clang was one of the first compilers to do that, and everyone copied them shortly afterwards, but really great feature there for kind of inline debugging of your code. We went over the syntax a little bit, but we want it to be fast. So Crystal generates native code, and what I mean by that is that the Crystal compiler will output assembly code. So there's no like intermediate compile to C or anything like that. It uses LLVM under the hood. LLVM is a compiler infrastructure project, so that's the tool set that other modern compile languages are built on. Things like Swift and Rust, those all use LLVM under the hood. But so here we have just an example of a compilation of a Crystal program, and then we can use some of these binary examination tools on whatever platform you're on, and you can see kind of what that method call looks like here in the generated assembly code. So it compiles to bare metal, if you will. The nice thing about that is there's plenty of tools already available for LLVM languages, so things like Swift and Rust, all of the tooling that those guys have put into making their languages and their binaries run fast, we can reuse all that stuff. So there have been some members of the Crystal community that like micro benchmarks, and they put together some of them here. And I realize that micro benchmarks aren't the end-all be-all of like what a language performs at. You want some real-world examples, but just to give kind of a little hint at the type of performance we're looking at here. When I said it was as fast as C, well, it's very close. Right? The important part is that we made humongous gains over our dynamic language there, like Ruby. Right? A factor of 10 in the runtime. And the other thing to point out is that the syntax between C and Crystal is drastically different, right? I don't know about you, but I would rather much look at this program that looks like Ruby than have to go and like, what is the C code doing? What am I reading here? Yeah, so this first example here is one of the Debian benchmark scheme. It's a Mandelbrot set generator. It just does some numerical calculations to kind of print out a little fractal pattern. The next small benchmark we have is a program that produces gene sequences in the FASTA or FASTA format. I've heard that both ways. But the point is that it generates sequences of nucleotides and plain text letters A, C, G, and T to represent organic molecules. And this is where C beat us by a good bit, but still seeing that very drastic improvement over a dynamic language like Ruby, and that's what we're after. Finally, this is a benchmark that performs a lot of numerical computations. It's doing multiplying of matrices. This is where C and Crystal have nearly identical performance, right? Look at that. We even beat it in memory. There's Python down there at 447 seconds of runtime. Well, that is a huge difference. And Ruby could not be shown here because it's probably still running. Well, that's the kind of speed that we're looking for in this language. This is a snapshot of the compiler and the standard library page on GitHub. The interesting thing to note here is I've pulled down this language toolbar here to show you that the compiler is fully bootstrapped, and what that means is it's written in itself. So this is really neat because you can go and learn about Crystal by just diving into the repository for the compiler and standard library, right? There's no better way than taking a look at what the Crystal guys are doing to write Crystal. And the other important thing to note here is that when you want to make performance improvements in this language, you just do it in Crystal, right? You don't need to fall back to C, right? So in a dynamic language like Ruby, or like Node, or even Elixir, right? You drop into C when you want performance. That's not a thing that you do here. When you want a more, performance-oriented implementation of like an array, for example, you just do that in Crystal. So I think that's really nice. So here's a list of things that we're going to go over for what the language does, kind of more in depth. Oops, sorry, there we go. I'm not going to read this to you because you can read items on a slide. So starting off here, this is an object-oriented language, and so the data types that we have in our program, everything is an object, right? There's kind of two main groups of data types in our program. We have things like value types, and value types are, they're stored on the stack. They're passed by value when you are using them as function arguments. And so these are things like Booleans and nils and characters. Various lengths of numbers, so we have integers of various data lengths, also unsigned types of those same numbers. Some more interesting types that are kind of baked in are structs and tuples and pointers. Tuples, being like fixed length arrays where you have safety of accessing indexes. And then the second group of types that you've got in the language is reference types. So this is what most types are in Crystal, right? So these are like classes. This is stuff that you are probably going to use pretty heavily. So things like strings or arrays or hashes, these are things that are allocated on the heap, and they are managed by the garbage collector. Ooh, that's a dirty word, garbage collector. How are we going to have a garbage collector to compile language? But anyway, I promise it works, and most types are this. So this is really one of the cornerstones of the language that I think is amazing, and this is really not seen frequently enough in other languages, and this is union types. So this is what gives us the feeling of a dynamic language without actually being a dynamic language. So this top line of code here where we have this array, and it looks like it's an array of mixed type, right? The first couple elements there are integers, and the second couple elements are strings. Hey, great, we got an array of mixed type. Well, it's really not that, right? It's really an array of one type, and the one type is a union type between an int32 and a string. So that pipe character there, that's what means a union type. Just to kind of hammer that point home, we're accessing one element of that array, and a single element is going to be, that same kind of union type, just unwrapped. And then the last line on this slide here, let's say we're trying to find a character in a string, and this .index method is going to give us either the integer index of where that character is, or it might be nil if the character is not present. So the return value of that method is going to be a union between int32 and nil. Yes? How do you access I'm sorry, I didn't. Oh yeah, so you would just use the same index notation, right? If you wanted to get to A, you would do A sub 2, and that would give you a string. Well, the value itself, right? So this A sub 0 or A sub 1 or A sub 2, all of those things would be this same type. They would all be the type of int32 or string. That is their type. In your code that you write, you can make that distinction if you want to, but so like in memory here, the way that that's represented is we store the type ID, and then we store whatever the value is next to it. So for the purposes of you writing code, most of the time you don't have to think about that, right? You can if you want to, but so you've just got this type ID here, this kind of combinator that you go and you look at and you say, okay, what do I really have here, right? And if you see that it's the ID for a Boolean, okay, I'm gonna go read this as a Boolean, and the language will do that for you just automatically, right? You can make more explicit what the type of things that you want are, but just by default, it kind of smooths this over for you. I don't believe that is a thing that the compiler lets you do. The like typecasting between different types. I was just typecasting. I don't believe the compiler will let you do that. I could be wrong about that, please. Right, yeah, so Crystal will make it where you are not incorrectly using the memory. You can do things like unsafe pointers if you really want to delve into that. But by default, if you're just using the normal access and variable syntax here, it's gonna make it where you're not gonna shoot yourself in the foot. Yeah, so we have the in-memory representation there. This is interesting, but this gives us a little bit of overhead, right? So for each value that we store, we've also got to store what is the type of the value. And so we can do better than this for reference types, for example. The thing that we can do is we can use a null pointer to represent a nil. And so in this case, there's no difference between this in memory compared to a language like C, right? It's important to mention, though, that in Crystal, all the types are non-nillable, and nil here is not a string, and it's not a thing that's in the type system. So we'll cover that more in depth in a little bit. So a feature from Ruby that you'll be familiar with, Ruby has great support for things like DSLs, domain-specific languages. This is something that we can still do in Crystal. This allows you to write a chunk of code that will yield its execution to some code that you give by a block. So in this example, this is something that would run 10 times. But in other dynamic languages that have blocks, you might incur a little bit of a performance penalty there. In Crystal, blocks are always inlined, so you get all the expressiveness of the block and good support for DSLs, but you don't have any performance penalty. Closures, when you do more, or sorry, procs, when you do more advanced things with the languages, you might need a way to have an anonymous function, or like a pointer to a function, or maybe you need a way for a callback to be stored, and so this is where you would come to procs, right? This is basically an anonymous function that you can assign to a variable, and then you can call it later by using the .call method. And so once you go above that, you can graduate to closures here, which is where this is very similar to a proc, but this is a type of function, and it uses the state from different lexical scopes. And what I mean by that is, so we've got this variable y, and it has been declared outside the declaration of this proc. And when we change y between different invocations of that proc, it's going to change the return value because we're referring to the scope outside of its definition. So that's neat. Not a huge deal. Just want to mention the language has support for that. Not really a cornerstone or anything, but something you may want, maybe. So method overloading. We've got types at compile time, and this lets us do all sorts of great things that we would normally have to do at runtime in a dynamic language. So over on the right-hand side there, we've got this ugly example of like, okay, let's pick apart these types that we've got, and how many things do I have in my arguments, and what are the types of my arguments, and oh, what happens when I don't understand my arguments. All of that just goes away because we can define method overloads based on the method signature, right? So the types of the arguments, the number of the arguments, or even the name of the arguments. So on the left here, we've got crystal code defining a couple of overloads for this sum method. And the other important thing to mention here is that the compiler is going to choose which one of the methods to call at compile time. So whereas in a dynamic language, we would pay a performance penalty and have to pick that apart every time that we call that thing in runtime, the Crystal compiler is going to efficiently choose what we actually want and compile it for us. So that's kind of the basic grammar of the language. And we like the smooth syntax, and we want to really enjoy writing the language, but we don't want to write a whole bunch of type annotations, right? We want all the power without the headache. So the compiler needs to do a lot of work for us to infer the types of our variables, the types of the stuff that we're putting into our code. And it's got to begin that type inference somewhere. And the place that it starts is it starts with literals, right? So when you come across an expression in your code and you're looking at one of these things, the compiler already knows the type of this thing, right? We've got built-in support for all kinds of different types. The one you might not be able to see down here is regex, so that's really neat. Yeah, so the compiler is compiling your program, and it sees one of these things. It will type that expression for you, and now you've got a foundation on which you can build the rest of your type inference for your program going forward. So we'll cover what that looks like here with assignment statements. So we know what the type of a literal is. What about a variable, right? So the thing the Crystal compiler does is it looks at our variable assignments. So each time that you have an assignment, you kind of make an expectation, right? So the variable here, this first line, A is expected to be able to contain whatever the value of the expression is on the right-hand side. So for this expectation, you're binding the variable A to be able to hold whatever the type of this expression of the literal one is, right? And we know what that is because it was a literal in the previous slide. It's an int. We can take that further. We can do variable to variable assignments, right? So we already know that A is an int, and if we assign that value to B, we're now making that same expectation of B that it can hold whatever A is. Right, so now we know that B is, we're expecting it to be an int. The Crystal compiler will also do more advanced things like track your types over multiple execution paths of the code. So let's say you've got an if statement, right? This might lead to a different expectation of what type of variable you've got here. So in this first path, we've got an integer, and in the second path, we've got a string. After this if statement has been interpreted, compiled, the compiler will merge the types from both branches of that and tell us that, okay, we see that you've done this assignment in both branches, and I can see from both of those types merged together that you're expecting A to be able to hold either an int or a string. Yes? If it's a single branch, you will need to handle the nil case. So maybe you're declaring a variable inside of the branch of an if. It will not do a union, but you'll have to handle the nil case, which we'll get into. I believe there's an example for that. Oh, I see. Okay, yeah. If you have the same type between the two branches, then that'll just give you the one type. Oh, got it. That is an error, right? So if you were to assign A42 and then also A hello in the same block, then that would be an error. You've made an expectation, and then you've subverted that expectation right on the next line. So here's an example of typing the method arguments. So first, you type the arguments. So if we're calling this add method here with 4 and 5, we can take those literals, and we can then infer from that our method arguments there, A and B, are going to be integers. And you can kind of think of this like a template, if you will. The compiler is going to instantiate us a version of this method that corresponds to the types that we've invoked it with. Right? So if we were to come along later in our program and call a different overload that we haven't explicitly defined yet, the compiler is going to generate one for us. Yeah, kind of like that. It does have generics, but this is also just a nice syntax way of having a method template, if you will. So going back to the, yes. Yes, concatenation there. This is string concatenation. The A plus B, that's concatenation, right? Going back to the nil example, so we've got some code here, and we're trying to pull out the index of the character Z from the word hello, and that's not a thing that exists, right? So we know that the return type of that method from a previous example is going to be either an integer index or it's going to be nil, but in this particular case at runtime it's going to be nil. And if we try to use that index to access something on the string, the compiler is going to tell us, hey, you know, there's no overload for nil. Here is the place that you tried to use that nil. In other programming languages, this would be a null pointer exception at runtime, but here the Crystal compiler has caught it for us. And so we don't have to deal with that, you know, blowing up in our face at runtime. The way that we get around this, though, is we use basically type refinement. And so there's a couple of ways we can do that. To refine this type. We want to basically eliminate the possibility of that index being nil. And one way to do that in Crystal is by using a conditional, right, an if statement. So for the scope of this body of this conditional here, the compiler now knows that the type of that index can no longer be nil. Right? So you're going to skip over that at runtime if it is nil, but otherwise you're going to run it because the compiler knows it's not nil. Another way to do this is with a more explicit Boolean check. So we could use the is a Boolean operator there. This is another case that's handled by the compiler. So just a couple of different ways to write that same thing there. Yes? It is not type coercing. It is making the expectation that if index is a nil, it's not going to do the block of the if statement, right? The compiler knows that it's not going to have to handle a nil case here because you've eliminated that possibility. Yeah, so no type coercion, just refinement, if you will, right? You're eliminating nil from the union. Okay, so if you were to do index.isa inside of this body here, you would get int32. You would get true. Right, so yeah, here's the type of this thing. Index is an int32, right? We've eliminated the nil. Moving along to classes, so we've covered you know, assignments and methods and all that stuff. Similar thing goes for classes when we want to determine the types of things like instance variables. So in Ruby, an instance variable on a class is denoted by this @ sign here. So for this constructor, we have restricted that constructor argument name to be a string. And so if we go along in our program and we assign that constructor argument to our instance variable, we're now making the expectation that our instance variable should be able to hold a string. And another way to write this in a more explicit fashion is if we were to just type it explicitly here. So at the top, we could give it an annotation for, I'm expecting name to be a string. And if I were to pass in something else here, like say I made a mistake in my constructor argument there and I passed in something else, the compiler would tell me, no, sorry, your types don't match, right? Tell me what you really want. So this is nice when you're designing. Maybe you want to explicitly type some things, but it's not always necessary, right? Sometimes you just want the freedom and the short syntax of being able to do it this way. But you could also explicitly type things if you wanted to. The Final thing that we'll talk about in type inference is that we have generated generic classes. So we even have assignments handled for those. This works in the way that you would expect, where when we are calling a new collection of this thing with this type, so the type is denoted by the capital T there, the compiler is going to generate us the classes that we want based on the two types that we called it with. All right, so we've got a nice syntax, and we've got a compiler, and it's willing to bend over backwards to figure out what the heck we mean, what our types of our variables are, and that's really nice. But so for good performance, though, we want concurrency. So in Crystal, the concurrency mechanism that we have is a lightweight abstraction of a thread called a fiber. This is a mechanism that's very heavily inspired by languages such as Erlang or Go. So this allows you to work without using mutex or other async mechanisms. And the way that this works is that a fiber is going to execute until it performs some type of blocking operation, right? Like maybe a slow network request, or you're writing on some slow I/O. And when that happens, your fiber is going to get scheduled out to allow some other computation to happen, right? And so then the scheduler, the language scheduler, is going to come back and pick up your thread once it's finished with its long-running operation. That is a great question, and I don't know the answer to it. Is it preemptive? I would have to get back to you on that one. Right. Yeah, great question. I don't know the answer to that. So the communication mechanism is channels, once again, very heavily inspired by Erlang and Go. So this is a thing that allows you to code linearly without callback hell, right? So we know callback hell being the thing where we've got a function and it needs to have us pass in a callback function for when it's successful, and we need to pass in another callback function for when it's failure, and we need another callback function for when it's both, and we don't have any of that madness here. You just code it linearly, and it does what you expect, right? You make the request, and then you have a variable that depends on the result of that request, and it'll just continue along linearly as your code completes. Maybe even if your fiber idles out and it gets scheduled for something else, execution flow continues in the linear fashion that you would expect. So in Crystal, we have great support for metaprogramming. So this is the thing that allows us to avoid boilerplate code, right? When I was talking about the ceremoniousness of like a Java or a C#, I don't want to write these accessor methods over and over again, right? This is something that I just don't want to write. It's a lot of typing. What if we could get the compiler to generate that for us? And so in Crystal, we can do that using macros. Macros are identified by the keyword macro, and then this curly brace syntax, which uses a subset of the language, is interpreted when you're running in those curly braces there. So this is basically text expansion, right? As long as whatever you're doing inside of this macro generates valid Crystal code, then you're good to go. So for this example, these two sides of this slide here are the same thing, right? Instead of writing the accessors manually, we define a macro that will generate a method that will be defined on the class for us. And it's worth mentioning that Crystal's macros are unhygienic by default. So that is, whenever the macro invocations are processed, the stuff that you do here, this generated code, is just placed directly into the context of wherever your macro is invoked. So really simple text substitution and great responsibility here when it comes to being able to do macros that don't, pollute your scope or clobber some other things that you didn't intend to, right? You can opt into that if you want to. You can opt into this, what they call fresh variables, when you use the % syntax. And so for here, the compiler is going to automatically generate you a non-conflicting identifier for you. So this way you won't unintentionally overwrite or maybe otherwise pollute the scope where your macro was invoked. So, I'm sorry, Elixir people. I know that you love your hygienic macros by default, but that's not what we chose here. Very much like in Elixir, though, the macro processor in Crystal can receive representation of the code in AST form, the abstract syntax tree. So this is the thing that allows you to access information about the methods, or maybe access information about the expression of this block, and you could do something crazy like shuffle the instructions around, right? Maybe you shouldn't actually do that. I wouldn't recommend it. But nevertheless, you can use a macro to do all sorts of crazy stuff with, defining methods for you. One final example of this, I'm sorry, not final example, got a couple more examples of this, is type introspection. So we know what our types are at compile time, and in this example, this is a macro that is going to reopen the struct from the standard library. So this statement right here, we are hopping into the standard library and we are defining a new equality operator. And the thing that we're doing is we're defining this equality operator based on all the types that we have for this struct. Right, so for every one of our instance variables, we're going to generate this line of code, and then we have our implicit return true at the end. So for this guy right here, it might not be exactly clear what's going on, so we can kind of step through it. We have a point struct, and this initialize method is the constructor. And so the thing that's going on here is we are telling the Crystal compiler that the point class has two instance variables. It has an x and a y, and they're both integers. So when this piece of code is processed here, when this macro is run, the thing it's going to do is it's going to generate us two of these return false lines, right? It's going to say return false unless our x is equal to the other x, and then it's going to have another one. It's going to say return false unless our y is equal to the other y, and then we're going to be done with the loop, and we're going to have the implicit return true at the end. Yeah, so this stuff here is compiled into your binary just right alongside the rest of the standard library. So that's really neat. One other crazy thing you could do with macros in Crystal is you could do something like run an external process to generate code. I don't know that I would recommend this, but you could do it that way. If you're looking for something like this, maybe the thing you're looking for actually is ECR. So one final way to automatically generate code is by using embedded Crystal. This is something that you're familiar with if you've used Ruby or Elixir with their embedded syntax. So basically you take a template and you have this template syntax and you generate a two-string representation of that template code. So in Crystal here, let's say we've got this method definition and our template. The thing that it's going to do is it's going to compile that template into our program, and it's going to look like this, right? We're going to have a bunch of these operations where we are writing those strings from our template to some type of I/O, right? That might be a file, that might be a network socket, that might be a whatever. But so this is one final way to do that. So the standard library in Crystal is pretty big. It's got all sorts of stuff that we would want for just general day-to-day use. So other languages where you might have to hop out to a third-party dependency management, there's pretty much everything you would want in the standard library here. So things like building command line tools or HTTP clients or servers, all that stuff is in here. I/O, the I/O library is stream-oriented. The design is very much like C, so you can read and write to I/O objects as like strings. The focus there is for reducing memory consumption. So like say you're wanting to generate a lot of JSON or like XML, and you want to just stream that out on the fly and not have to build up a whole big giant buffer in memory to do it. Package management. In Crystal, the package manager that's built in is called shards. You can go to crystalshards.xyz to see kind of a directory listing of all the shards that are available, the third-party packages for this language. Some of the things that are in there are things like database drivers. For example, Postgres. If you wanted to talk to a Postgres database, there's a shard in there for that, and it does not have any C library dependencies, right? The Crystal library for Postgres is just written in Crystal itself. It knows how to talk the Postgres protocol, and it just writes directly to the socket, so no C compiler or no C library dependency necessary. If we wanted to, though, we could talk to a C library because, let's face it, it's not going anywhere anytime soon. So the way that we do that is we declare bindings in Crystal itself. So like here, we've got a C function, maybe from the math library. And the thing that we would do is we declare this binding to the C function, and then we're able to call it in our program in this way. We could do more advanced things like declaring structs that exist in kind of the C memory layout of things. And so the way that we would do that is in Crystal itself. We would use the syntax to declare it, and the Crystal compiler, since it knows LLVM, is going to use that very heavily to handle all the going back and forth for you, right? You don't really have to think about it a whole lot. It's going to generate the code that knows how to have the C-style bindings for that. One final thing to mention on interacting with C is that there is support for native callbacks. So this particular example, this is a C function signal, and it accepts a callback function there in the very end. So this can be very useful for maybe binding to UI library, for example. If you wanted to receive a callback, when someone clicks on your button in your application, this is something you can do as well. And here we've just got like an inline kind of proc syntax for passing that in. All right, so wrapping up, we have Ruby-inspired syntax. Compatibility is not a goal, though. We have LLVM, which provides us great tools for this compiler and for its runtime. We have Crystal being inspired by many languages, Erlang and Go in particular. We want to learn from these modern languages that do things right. And we also want the compiler to do as much work as possible and hopefully inspire languages in the future. As far as the community goes, there is a mailing list, there's a couple of chat rooms, there's all sorts of great stuff. You can go in there and you can get support from community members, right? Not just the company that created this Manas, but all sorts of different people on there. A bunch of contributors to the compiler and the documentation. They have really great documentation if you go online and look at it. That's a thing that they really care about, which is nice. Coming from a language like Rust, I really appreciate it. And Crystal is sponsored by really anyone who wants to give them money, right? So even up to as little as $1 a month, they would be happy to receive your contribution. So going forward, what do we not have in this language? The thing that we don't have in Crystal is parallelism. So we went over concurrency, but in Crystal, those fibers, those are executed on a single thread only. And so the thing that is coming here in 2017, which is going away quickly, is true parallelism, where we could have multiple fibers running across all the cores of our machine. So yeah, when we looked at benchmarks, all of those benchmarks were for single thread performance. So I think we'll see some pretty good performance after that. Crystal is coming to Windows. It only works on Unix-like platforms for now. And then they're going to polish up other language features like the standard library, stuff like that to reach 1.0. So the future for maybe something that I'd like to see going forward is WebAssembly. All right, so there's this thing called WebAssembly. You guys have heard of this. It is a binary format for the web. You can use it in your browser alongside JavaScript or maybe in place of JavaScript. And so the thing that Crystal has is it's built on LLVM, right? And LLVM can generate WebAssembly binary format. So what the heck am I doing still writing JavaScript for my browser? Like, what's going on here? Unfortunately, this is not a simple task. LLVM is kind of a bit tough to work with, and it's been a hot minute since I last wrote or dug into compiler internals. So once we iron everything out here, I think we might have a chance to eliminate this foul beast once and for all. So if this is something you're interested in, please come talk to me, and we can work on that. But otherwise, I think that concludes our talk. So there's all the Crystal information there. Here is me at Delegator. I'd like to mention that we're hiring. If you go to our careers page there, there's a couple of listings there, one for a PPC account manager, another for a part-time or contract web developer, and you can find my personal information down below. And that's it. Question?
I think I just hit Siri. So I guess at the end with the coming 2017 thing with parallelism, this kind of might answer the question in the future. But so I guess I was kind of wondering what the typical use case for Crystal is. I mean, obviously they talk about the performance stuff, and that's cool, and it showed numbers for single-threaded stuff and HTTP requests and stuff like that. But I would think that the reason you'd want to use C for something is having access to multiple cores to be able to, for something like large matrix multiplication or a ray tracer, we're just doing linear algebra or whatever. So I guess this is kind of maybe gonna be answered.
Yeah, so definitely the performance thing is something they're concerned with. They will address parallelism in the way that you expect, where you do want to have access to all the cores. So where this shines currently, though, is things like command line applications. Those work really well for Crystal. It can do web stuff. I don't know that I would recommend it yet. It's kind of new for that. Maybe not all the great frameworks that you would expect exist there yet. But yeah, I mean, it's general purpose, so really any of the things that you would want performance for, maybe you don't even care about performance. Maybe you just want a nice syntax and some performance gains. You could deal with the single-threadedness of the language, so that's where it kind of shines. It's general purpose, so use it for whatever. Yes?
So Windows 10 has, you can install a Linux from Microsoft. Will that work with this? Or do you have to have a true Linux?
Yeah, so if you were using a, like the Windows 10 bash on Ubuntu on Windows type of system, that would be enough, I believe, to satisfy the Unix requirement for this. I believe you could use the normal package manager to install this language, and that would work just fine.
Yeah, so I by no means, I'm a total noob with Golang, but like kind of the overall, the advantages you're pointing out in this language remind me a lot of it. They're both garbage collected languages that are compiled, but meant to be much easier to use than most compiled languages. So I'm just wondering, particularly with Go already having probably more popularity and broader platform support, like where does Crystal Lang really shine over Go?
So I think the answer to that question is it really shines in syntax, right? So some of us who might be turned off by the Go curly brace stuff, or maybe the other type of thing that we have to do in Go to get it to understand what we mean. That's where Crystal really shines in that it has a much more Ruby-like syntax. It's more familiar. It's a more complex language. I mean, I guess do with that what you will, right? Go is very simple. But some of the features here are things that I know Go has been asking for a very long time and may never happen. So yeah, really just syntax difference. You could think of this like the Ruby, but Go compiled like, yeah.
For the binary distribution of the binary, can it be compiled static so that you don't have any libraries you have to install?
Yes, there is static compilation in Crystal. It is not super straightforward right now. That's one of the things I'm hoping they'll smooth out in the future. But yes, in theory, that is possible to statically link to your libraries that you depend on. Any other questions? Great, thanks everyone.